Alright, in this video we are going to expand on the idea of power series, which recall that a power series is a series in the form where it'll have some constants out in front times x minus some centered value all raised to the n. And power series start at 0 to infinity. So a certain type of power series is called a Taylor series, and this is a certain type where the a sub n's are of the form the nth derivative evaluated at c all divided by n factorial. So clarification here, this nth value right there, that is the nth derivative. And the 0th derivative is not a derivative at all, so it's just the function itself. And then the first derivative, second derivative, third derivative, etc. of the function. So that specifies the nth derivative for each term in the series. Then this c value here, it's not that you're going to multiply by c, it's that you evaluate. Actually, let me even clarify that further. You plug in c into the derivative. Plug c into that nth derivative. So that's that top value. You find a bunch of derivatives and you plug c into them. Alright, so I'm going to show you how this kind of works and how this is all true. So we're going to start with some function, and we know that we can represent a function with a power series. So we can represent a function as the sum from n equals 0 to infinity of a sub n, sorry I ran out of room right here, x minus c to the n. We're representing it as a power series. Now if I expand that power series, meaning I'm going to plug in 0, plug in 1, plug in 2, and add everything together. When I plug in 0, I get a sub 0. When I plug in 1, I get a1 times x minus c. When I plug in 2, I get a2 times x minus c squared. When I plug in 3, I get a3 times x minus c cubed, etc. I'm going to take some derivatives here. First derivative, all of these a's are constant, so the derivative of a naught is 0. So the derivative of a1 times x would leave me with a1, because that's a number out in front of x. For the next term, the 2 would have to come down in front of a sub 2, and then that would be multiplied by x minus c. And then for the next term, the 3 would come down in front of a sub 3 times x minus c squared, and then this would continue. I'm going to take another derivative. a1's a constant, it goes away. Out in front of x for that next term is 2a2. On the next one, the 3 comes down in front. I'm sorry, the 2 comes down in front, so it's 3 times 2 times a sub 3 times x minus c, and then that would continue. And if I take all of these derivatives now and plug, actually, do you know what? Let me do one more. Let me do a third derivative here. So a third derivative, the constant would go away. We'd be left with 3 times 2 times a sub 3. And if I had another term in here, I would be left with a 4 times 3 times 2, because that would have been a 4 from this first one up here that would have gone down in front, and then the next one would have been a 3, and then the next one would have been a 2. Okay, so that times a sub 4, and I would now be at the spot where it's just raised to a first power. So I put in an extra term in there just to kind of make a point here. And what I'm going to do now is plug in c into all of these. So if I take f and I plug in c into it, notice that I've got a bunch of x minus c's, and every time I have one of those, it's going to go away. It's going to go to 0, because c minus c is 0. So what I'd be left with in just the function is a naught. What I'm left with in the first derivative is just a1. All the rest of them have an x minus c. They go away. In the second derivative, I'm left with a 2a2. In the third derivative, I am left with that 3 times 2a3. If I solve for the a's, so a naught is equal to f sub c. a1 is equal to the first derivative. a2 is equal to a second derivative divided by 2. And a3 is equal to a third derivative. And these were, I forgot that evaluated by c and that one above, but that's okay. Third derivative evaluated at c divided by 3 times 2. And I could summarize all of these. If I kind of brought them down into a general term, I could say that these are all an nth derivative evaluated at c divided by n factorial, if n starts at 0. Because for this first one, it's the 0th derivative, which is the function, divided by 0 factorial. This one is divided by 0 factorial. This one's divided by 1 factorial. 2 is the same thing as 2 factorial, and 3 times 2 is 3 factorial. So in the denominator, I have 0 factorial, 1 factorial, 2 factorial, 3 factorial, etc. That's n factorial. And then in the top, I've got f0 evaluated at c. It's the function at c. F prime of c, f double prime of c, the third derivative at c, the fourth derivative at c, etc. And that would be the nth derivative of c. And this is where all of these a sub n's come from, which is right here in that Taylor series. If you look at the table of all the convergence and divergence of series, it has this Taylor series on the lower right-hand part. And so it defines these a sub n's. So Taylor series are specific power series with separate a sub n's in them. Now, if it so happens that c is equal to 0, so if it so happens that c is equal to 0, you get what's called a Maclaurin series. And the only thing that's really different on the Maclaurin series is then it's just evaluated at 0 and not some other number. And then, of course, the c goes away because c is equal to 0. All right. So a little bit of a summary here. Maclaurin series is a Taylor series where c is equal to 0. And Taylor series or power series where the a sub n is very specific at those nth derivatives evaluated at the center divided by n factorial. And so you can think of this as sort of like a hierarchy, I guess, with Maclaurin series being the most specific and power series being the most general. And don't forget that power series are polynomials. It's a polynomial representation, sometimes written in summation notation and sometimes not, for functions, because we can do things easier with polynomials than we can with some functions. All right, this table is in the right-hand corner of that sheet, and it gives a bunch of known Maclaurin series. So on all of these, c is equal to 0. So they're all centered at 0, and you can see that with all of the x's. And what this is doing is taking a bunch of different functions and showing how they could be represented as a polynomial. So e to the x we can represent with a polynomial, sine of x we can represent with a polynomial, etc. On the right-hand side of this, it gives the interval of convergence. And we did some of this with power series before, where whatever you have for x in the function there, you would put in for x there. And so it would, and I think the one that we looked at before mainly was this guy. And we did lots of examples with that. So whatever you had for x in the function went into the x for the interval, and you could just find the interval from that. You didn't have to check endpoints or anything. All right, so let's do an example, and let's actually do an example where we, sorry, I didn't want that big of a line. Let's show that e to the x is true. And so let's do an example, and let's show this guy. And we're going to show it using the definition of Taylor series. So we're going to show that by finding the sum from n equals 0 to infinity of the nth derivative. Now this is a Maclaurin series, so we're going to plug in 0 all over n factorial times x to the n, and x to the n because c is 0. So these are Maclaurin series. All of these have c equals 0. Okay, so we need a bunch of derivatives. Our function is e to the x. So if we take a derivative of e to the x, we get e to the x. If we take a second derivative of e to the x, we get e to the x. And then if we take a third derivative of e to the x, we get e to the x. So now let's plug in c. c was equal to 0. If we plug in 0 into e to the x, we get 1. If we plug in 0, this is the first derivative now, into e to the x, we get 1. If we plug in 0 into that second derivative, we get 1. You can see the pattern here, of course. So each one of the nth derivatives evaluated at 0, they're all just 1 in this case. So if I plug that into the sum, 1 over n factorial times x to the n. Done. You can see that's what e to the x is for a Maclaurin series up there. Right, so that's how Taylor series works. That's how all of these were developed, is by taking derivatives. Now that we have known Maclaurin series, we can use them to find all other Maclaurin series very similar to what we did with power series. Well, this is exactly like what we did with power series. So as an example, let's find the Maclaurin series for f of x equal to x squared plus 2x e to the x. Now we know that the Maclaurin series for e to the x, we just found that. And even if we didn't find it, it's on the table. Sum from n equals 0 to infinity of x to the n over n factorial. And so what we need to do with this sum is multiply it by x squared plus 2x. Now because of the plus there, I'm going to have to kind of distribute that sum through. So this would be x squared times the sum from n equals 0 to infinity of x to the n over n factorial plus 2x times the sum from n equals 0 to infinity of x to the n over n factorial. And then I'm going to combine the x's on both of these separately. So on the first one, if I combine x's, it would add 2 to the exponent. And on this second one, there's going to be a 2 out in front, but it only adds 1 to the exponent because we just have an exponent of 1 for those x's. All right, so we can now take any of these known Maclaurin series and manipulate them in different ways to find other Maclaurin series or other Taylor series. So another example, we're going to use a Maclaurin series, which remember is centered at 0, to find a Taylor series. So a Taylor series centered at 3 for f of x equals 1 over 1 minus x. Now, we have a Maclaurin series. A Maclaurin series for this function right here. It's the sum from n equals 0 to infinity, and you might have to look at the sheet. It's just the sum of x to the n. All right, so we're going to use that, but it has to be centered at 3, and a Maclaurin series is centered at 0. And so we have to do this shift because what we want at the end of all of this is we want x minus 3 to the n. We want them to look like that. So instead of an x in here, I'm going to want an x minus 3. So, but I can't, this function right now is definitely not the same as what we started with. And it needs to stay the same. I need to keep equality, but I want x minus 3's. So essentially what I've done in putting this x minus 3 in there, essentially what I've done is, because of the minus and the minus, I've added 3. So because I've added 3, I'm also going to subtract 3 from that denominator, and then I now have an equality here. If I distribute the negative, I have a plus 3 and a minus 3, and it leaves me with 1 minus x. All right, I need to rewrite this, and now the whole time through this, I need to keep the x minus 3's. So I'm going to combine the 1 and the negative 3. Negative 2 minus x minus 3. Now I still want to use this same Maclaurin series, but now I need a 1. And because of this whole shifting, I don't have a 1 anymore. But I can factor out a negative 2. So 1 over negative 2 leaves me with 1 plus x minus 3 all over 2. Because if I multiply through by the negative 2, I get negative 2 minus x minus 3. Yep, so I still have kept equality here. And now it's in a form that I can use. And if you look at the sheet, you would see that 1 over 1 plus x is equal to the sum from n equals 0 to infinity of negative 1 to the n, x to the n. All right, so I'm going to use that here to write this sum from n equals 0 to infinity. I have a negative 2 in a denominator, so essentially that's a negative 1/2. The formula has a negative 1 to the n in it right there. And then I've got an x to the n, but this time I don't have x. I've got x minus 3 over 2. So I'll have x minus 3 over 2, all to the nth. And let me kind of gather some like terms or like stuff together. For instance, I've got a negative 1 out in front and a negative 1 to the n, so that would combine together to give me a negative 1 to the n plus 1. I've got x minus 3 to the n in a numerator. In a denominator, I've got 2 to the n and another 2 out in front from the 1/2, and so that would add 1. So here would be my Taylor series for that function, which if it was a Maclaurin would be really simple, but we had to shift everything around to make it centered somewhere else. We could have also taken a lot of derivatives and then found a general term for those derivatives. So if we could have put them all into a general term of the derivatives divided by an n factorial, we should have gotten this, the -1 to the n plus 1 over 2n plus 1. All right, one more example of what we can do with Taylor series. Let's express the integral from 0 to 1 of the cosine of x squared dx as a series. Now, this is an integral that we don't know how to integrate this. So what we can do is put it into summation notation. We can use a power series. We can use a Maclaurin series. We can just make it centered at 0. And then we can integrate that series because it's a polynomial. It's pretty easy to integrate. You just add 1 to the exponent, divide by that number, just like you would with like x squared. All right, so the first thing we need to do is find a series for cosine of x squared. Now look at the right-hand side of that table. There is a series for cosine of x. The cosine of x is the sum from n equals 0 to infinity of -1 to the n, x to the 2n, but we don't just have x, we have x squared. So I'm going to raise that to the 2n, and then it's divided by 2n factorial. So now, if I integrate this, the sum from n equals 0 to infinity of -1 to the n, x to the, let's combine those. So we would multiply those two together, we'd get 4n, all over 2n factorial. And we're going to integrate that with respect to x. So when we integrate it, the only thing that we have to look at are the x's. Everything else is a number. So to integrate, we are going to just look at the x's. We're going to add 1 to the exponent of the x's and then divide by the exponent of the x's. Like if it were x squared, we'd get x cubed over 3. And we still have the 2n factorial in there. And that is a 2 and n, or 2 times n factorial. Now this is a definite integral, so we're going to evaluate it from 0 to 1. We just integrated with respect to x's, so the 0 and the 1 goes into the x's. So if we plug in 1 to the anything is 1. 0 to infinity, so I'd end up with -1 to the n, all over 4n plus 1, 2n factorial. And if I plug in 0, I get 0, so I would just subtract 0. So there's my answer. There's how I could express that integral as a series. And if we want to, and what this means is that we could write out this integral from 0 to 1, cosine of x squared dx. This is equal to this sum, and if I plug in some numbers here, so start plugging in some numbers, so it's 0, that's going to be a positive term. The bottom, 4 times 0 is 0, plus 1 is 1, and 0 factorial is 1, so I just get 1. The next term when n equals 1 is going to be negative because of that -1 to the n. When I plug in 1, 4 times 1 is 1, plus 1 is 5, and 5 times 2 would be 10. And then we would add to that the next term, which is going to be positive 1, and I'm plugging in 2 this time, so 8 plus 1 is 9, and I would have then let's see, 4 factorial. So I'm not sure exactly what that would be. 4 factorial is like 24, so 24 times 9. Minus, so 0, 1, 2, 3. We're plugging in 3 now. It's a negative. 3 times 4 is 12, plus 1 is 13. 13 times, I always lose my spot where I'm plugging in. 0, 1, 2, 3. 3 times 2 is 6 factorial, etc. If we added up all of those numbers together, we would get the exact integral. If we stopped at some point, we would get the approximate integral. And you can see that these numbers are going to get pretty small pretty quickly. And so this one is not too bad. You can actually approximate integrals this way. And this is a tool that is used a lot to approximate integrals that are not integrable.